Hey everyone, I am making a video on going over how to find volumes using triple integrals and be able to draw different planes in 3 dimensions, and trying to show you the pathway on how to find your limits whenever you're trying to do triple integrals. What things to look out for when trying to do this. Um, to help give a better visualization on what each step really means, and to better understand the process instead of just kind of sitting there, kind of confused, because that's the way I was when I first learned this, and I absolutely bombed this on my exam. I had no clue what I was doing. Um, the question is asking to find the volume of a region in the first octant. First octant meaning only the positive areas. So it's going to be this little like square, and this like the positive, X, Y, Z. So we're kind of looking in this region here. And it's bounded by two cylinders. So that the cylinders parts is important, because these equations that you see in the blue and the green, these things are being projected like out from their plane that you see them. Like this is the first equation that's blue, is y equals 4 minus x squared. Well, this is an equation that's in, like, you can see this at just the y-x plane, but it's being projected in the z direction. And I'll be able to show you that in this. So we're given this y-x plane to draw out the y equal 4 minus x squared. So when we do that, and it's only in the positive areas, since we're only dealing in the first octant. So when we draw this, we're going to have a height of 4. So we have 1 point here at 4. And it's a negative x squared, so it's going to make a parabolic shape, but downward. So we're not including the negative half in the negative x direction, for the reason that it's only in the first octant. So this here is y equal to 4 minus x squared. And we can draw this shape like in the y-x plane on this 3-dimension, like the showing off 8 octants section. So you just kind of have to look at how you drew it in the y-x plane and recreate it. So it's high up here, and it makes that same parabolic shape down to the x. So this is what the shape looks like in the y-x plane, up and down the cylinder. But it will be colliding with another cylinder at the xz plane, which is seen x squared plus z squared equal to 4. Since it's x squared plus z squared equal to 4, we can imagine that that's a circle, because it's got your one variable squared plus another variable squared equals r squared. So with r being 2, so it makes our r squared 4. So when we go to draw this, we're not given a plane to do it, but you could draw your own like xz plane to see what it looks like. But it's not too terribly difficult to imagine. So we're to look back and make sure that this plane, the cylinder, the x squared plus z squared cylinder, lines up with the y equal 4 minus x squared cylinder. We can just look at the points on the y-x plane. So we know that this point here at the top is 0, 4. This point at the top, so you put it, we know that y is going to be 0, so we put y is 0. We have x squared equal to 4, which means x is equal to 2. So we know that this is 2, 0, which is good, since we know that if our r is equal to 2 on the other plane, or the other cylinder, then we know that these points are going to match up. So right here is going to be 2, 0, 0. Then the circle will be going around with its radius until it hits z, and this would be 0, 0, 2. I'm sorry, got a bad cough right now. So both of these planes are going to be projected like perpendicular to the plane that they're in. So the the one in the XZ plane is going to be going in the direction of the positive Y. The one in the YX plane is going to go in the direction of the Z, positive Z. So as we draw it, oops. Oh, hold up, my bad. I forgot that part's erasable as well. Where's there we go. Alright, I'm just gonna not worry about the little line. So we can project this laterally to the Y, and this goes up as well, parallel to the Z. And there's going to be some barrier. We don't know exactly what the barrier is yet, but we don't need to know it for now. It's going to be in between these two planes, the blue plane and the green plane. So we can just draw it like this for now. So then we can see, and I'm going to just better show all the different points and what this thing looks like. This point here is 0, 4, 0. I'm going to color the planes with the color that I made the equations. So for the blue, the y equal to 4 minus x squared, this is this plane. And the other plane I'm making green is this one. So it's it's not too terribly difficult to see what the shape looks like. It's like there's actually no way to describe it. It's just two planes colliding together. But we get this region by how these two cylinders collide. You know, the blue one goes in the Z direction and it hits the green one, which is going in the Y direction. So it creates this boundary plane here. And later on, like the next section is going to ask to find that. But to find the volume, we need to be able to project whatever our D, the orders in our D's to find whatever planes we hit. So when we're doing DZ, we shoot our arrow up in the Z direction. And when we do that, we first hit Z equal to 0, which is the XY plane, essentially. And that's because our boundaries is also the planes that keep it in the positive, area, the positive octant. So ZX is a plane, ZY is a plane, and XY is a plane that is a boundary for this region. So when it comes up, it first hits Z equal to 0. So we can write Z equal to 0 over our triple integral since we're first solving for Z. Then when it exits out this green plane. So it means that it's going to be exiting out x squared plus z squared equal to 4. So if it's exiting out that one, then we need to write this equation in terms of z. Solve for z in terms of x. So this implies z equals the square root of 4 minus x squared. And the reason why it's a positive square root is because it's in the positive octant. So we don't need to worry about the negative or doing absolute value, or plus or minus or anything like that. So that makes this 4 minus x squared. The next part is finding our y. So y is going to be the very same thing, where we take an arrow in the positive y direction. We first hit the zx plane, which is y equal to 0. Simple enough. And now the next part is we hit this blue plane. It'll come out right here. If you can see the little blue, the little pink X in the blue region. So we're hitting y equal to 4 minus x squared. There's no algebra to do, so we can just write 4 minus x squared right here. And then the last part, we have to worry about our x values. Where is x going to and from? Since now we've already covered all of our planes and all of the equations that we need to account for in finding the volume, all we care about is where x goes to and from. So x, when it hits this plane, x is at 0. When it hits, going out here, that's the arrow. Whenever it hits the zy plane, x equals to 0. And whenever it exits out the either of these two planes, x is going to be 2, since it's the very end point that we have in the positive direction of x. So it's going to be x equals 0 to 2. And you can solve the volume on your own, but typically, I know for ENGR 201, they typically don't make you solve for the volume unless they set up a triple integral for you to do. So this is all the typical work you have to do. They just try to make sure that you can find the limits of integration, and this is done by being able to draw your figure in 3 space and draw the arrows to show what is hit at what like what planes. So this next part is going to focus on this boundary that we drew right here. You can see we have to find the equation for that boundary. So in order to find the equation for that boundary, we just have to look at in what direction do we see both planes. And what I mean by that is, if you look at the top, like looking down from the Z, so like if we have our face right here, and we're looking down, we really only see the XY plane. We only see the XY plane, so we only see this green plane. We don't see both planes yet. So it's not something to look out for. And when we look out from the positive Y over here, we only see the blue plane. So we don't need to worry about that one either. But when we look over from the X, I'm going to put a sad face because it means we have to do extra work. Now, so when you go this, you see both the green plane and the blue plane. So this means that you see some boundary line. And for the looking up at the top or from the Z or from the Y, you see the boundary, but you can't tell it's a boundary. You only see this as either the top boundary for the blue, or you see this as the right boundary, or like another boundary for the green, but you don't see the blue and the green touching each other at this boundary. So in order to find it, as we just, like I said, we have to look at from the direction that shows from the X, since you're able to see both. So we're going to look at the ZY plane. So we need an equation that relates x squared plus z squared equal to 4 and y equal to 4 minus x squared in terms of y and z. We're essentially cutting out the x. So an easy way of looking at it, so since we have x squared plus z squared equal to 4 and y equal to 4 minus x squared, we can just solve for x squared and subs one in for the other. So I want to solve for the x squared in the bottom one. So I have x squared equal to 4 minus y. I want to substitute it into the top one. So then I have 4 minus y plus z squared equals to 4. So this implies, and you can cancel out that 4, the 4's on both sides, since we have a positive 4 on both sides, and I move the y over. So this implies that the boundary is y equal to z squared. And this boundary is projected into the z in the x direction. So when we're looking at the zy plane, this boundary here is cuts through both the cylinders. This y equals to z squared. And now we're going to use this in order to find the volume in a different order that requires us to do a double triple integral. So essentially 6 integrals. Thank God we don't actually have to solve for it. So I want to go ahead and draw a plane to use in order to better visualize the integral. Sorry. Thought I picked this out. There we go. I like working in pink, so let me go back to that. Alright. So like I said, we're working in the Z. Ooh, if it's going to let me write. I guess not. There. Wow, it's awful. Man. Okay, there we go. I don't know what's going on. Alright, so since we're working in the ZY plane, I'm going to go ahead and draw our boundary line, y equals z squared. So it's going to be a parabolic shape. And again, we're only working in the positive area, so we don't have the negative side of it. So it's really like, it's more like the positive square root of y, if you want to look at it that way. So it's more like z equals the positive square root of y. So we have that. So then we have our two other cylinders that project up in the positive z direction. So I'm going to draw that line right there to represent the cylinder coming up in the z direction, and this cylinder coming in the positive y direction. And I want to draw the lines that match up with the figure above to help us better understand this picture. So here is the blue plane. There you go. And here is the green plane. Alright, see how that matches up? And then we're looking from the x towards like the two planes merging. So if this right here is x squared plus z squared equal to 4, this right here is y equal to 4 minus x squared, and our boundary is y equal to z squared. So now we're going to use these three equations and this graph here in order to find out the volume using in the order of dx, dz, dy. So I want to use the blue region first. So I want to just highlight, or like just mark it blue. So this is the blue part. Oh, here, I'll put it closer to this is the blue part. This is the green part. So we're essentially just doing this integral into two different regions, which is divided up by that y equal to z squared, plane. So looking at the blue one, I'll do dx first. So dx, so like since we gotta kind of come back up here to see it. So we're going to go hit x equal to 0 because we're hitting that zy plane. Then when we're coming out, we're hitting the blue plane. So when we're hitting this blue plane, we're actually hitting y equal to 4 minus x squared. So we can rewrite y equal to 4 minus x squared as x equals, let's see here, 4 minus y, the square root of 4 minus y. Yeah. Alright, so since we've done the x, now we can move on to the z. So in the z, we look at this graph over here and, project our arrow upward. So since we care about the blue region, we care about where we enter and where we exit the blue region. So since we enter the blue region at z equal to 0, we write z equal to 0 here. But we exit the blue region at y equals to z squared. And we can rewrite this as the square root of y, since we went in terms of z. And lastly, we're going to do y, which is going to be from y equal to 0 to y equals 4. Since this point here is where y equals 0, and this point here is y equal to 4. And we can look back up at our graph to see that 0 here, 4 here. It's about caring about the very last part of the integral is always, for like the limits, is always about what values, the min and max values essentially across the region you're integrating. So it's going to be y equal to 0 to y equal 4. So this green part, you now have to look at how our arrow enters and exits the green part. For the, sorry, I got to do the x. So going back up here, since it enters at x equal to 0, like the first one, right, x equals 0 here, but it exits into the green region. So we have to rewrite the green region in terms, it's all for x in terms of z. So we have to rewrite this one here as x equals 4 minus z squared, but underneath the radical. Because, and we can keep it positive because this is just a positive octant. So we can say the square root of 4 minus z squared. Alright. Because that's just to show you, like, it's this arrow is coming out of the green here. That's for both of the blue and green. Like, it's going into the ZY plane and out one of these green or blue regions. And that, if that helps like illustrate what we're doing here to find the limits. So now I have to do, oh, I'm so sorry. I just realized I just wrote the limits on the very last integral. My bad. So sorry, now it's to do z. So for z, again, we look at the green region. So we go at what we enter and what we exit the green region. So we enter at this boundary line. So we can say z equals the square root of y. But it exits z squared, x squared plus z squared equal to 4. So we can rewrite this equation as z equal to 4 minus x squared. Oh, sorry. Sorry. We don't write the equation. My bad. We write what the value is for z here. So z equals 2. Sorry. Since we already accounted for the x in the first limit, we don't need to worry about this equation again. So we just have to worry about what this z equals at that point, which is z equal to 2. We can look back up here and show that this, as we go in the z direction, this is z equal to 2 because it's at 0, 0, 2, and that's the highest it gets. So square root of 2. And now we have to account for our y. So for our y, again, we just look at our minimax values. You know, it's at 0 to 4. So when doing the double triple integral, your last limit of integration should be the same. And your second limit of integration for both of these should have the boundary line in it. So with the blue region, the boundary line is accounted for at the top. In the green region, the boundary line is accounted for at the bottom of the second integral. But the first one, the first limit of integration, so looking at this as first, second, third, just to show you all what I mean. The first one always accounts for the different planes you're doing. The second accounts for the boundary in which you first enter and exit the two different regions, with what, like the second one should always share the boundary line in it somewhere. So either it enters the boundary line or it exits the boundary line. In the last one, they should be the same because you're accounting for the same, like, last limit, like the min and max values. I hope this is helpful. It takes time and practice because to understand what's going on when finding volumes. I was not perfect at it, but once you understand, it solidifies and it gets easier, much easier. So hope this helps a lot. Glad I could help. Oh my god, I'm trying to figure out how to stop this. I don't understand. There it goes. Alright. Good luck on your test.